Okay, thank you, Robert, and thank you, all of the organizers of this. I appreciate that I'm going first in this block so that I'm not the one holding you back from lunch. Anyway, yeah, so as Robert said, I'm a principal engineer at Deepsig and the technical lead on our Okudu program. And I think basically everything that I am going to say has already been said by at least one person here. And I kind of want to reiterate that Okudu and OAI sort of, we're not, I don't know, competitors in any way. I think that we can sort of learn from each other and kind of use one another to really create some pretty good software. So I'm going to just sort of talk a little bit about what Okudu is, how it kind of fits into this ecosystem, and what Deepsig's role is in kind of guiding the development of this project. How we're using OAI UE at Deepsig, specifically in our kind of 5G, NextG, AI RAN testbed. And then talk a little bit about kind of if you were our testbed engineer and we're told, well, get OAI UE working with Okudu Gnode B, what sorts of like issues would you run into, and kind of how has the recent developments undertaken in OAI kind of facilitated this kind of working out of the box more or less now? So Okudu is a relatively new project. So the goal is a carrier-grade open source ORAN Gnode B. Carrier-grade is a little bit of an ambiguous term. I'm always a little bit annoyed with it as an engineer. I think that probably it's best defined kind of in sort of hindsight. A Gnode B or any sort of stack here kind of becomes carrier grade when it is adopted by a carrier. And so that is kind of the goal of this program from the kind of high political level down to me and all of us at Deepsig that are working on this. It's a completely independent code base. It sort of evolved from the SRS RAN project, which I think many of you were sort of know about. And SRS is still pretty closely involved in the development process for Okudu. The goal here is to, as much as possible, embrace all of the sort of ORAN community standards. So all of these F1, E1, E2, O1 interfaces with FAPI support, so split 6, and as well as support for kind of ORUs and a variety of different SDRs. I think right now it's mostly limited to USRP, but I think that there's some interest in adding support for additional radio units or software-defined radios. And just to kind of, again, emphasize that, yeah, OAI now has its own Linux Foundation project. Okudu's organized under Linux Foundation as well. Duranta and Okudu kind of have their own mission statements. Duranta kind of fills the need for kind of a research platform that has a lot of different use cases that are satisfied within that software stack. Okudu, on the other hand, the kind of main goal is this kind of carrier-grade platform that's ready for commercial deployment. And so, yeah, as I said, I think that these are kind of complementary goals. Yeah, so there is I mean, this is part of the documentation on the Okudu project website, but there's a very well-defined roadmap, and I kind of show this here to indicate. I mean, if you look through this list of items, many of these are already supported by OAI. But the kind of scope of SRS RAN and now Okudu was always a bit smaller. And so kind of these are kind of the targeted improvements that we're looking at over the next couple of years. So the initial release was in April of this year. So this is version 26.04, just like Ubuntu and a lot of other projects, it targets kind of this 6-month release cadence. So the next major release is coming up in October. But kind of the guidance at this point is that if you want the best and the newest, go sort of build the development branch, because there's currently a lot of ongoing work on that. So yeah, where Deepsig comes in is that we're trying to kind of build out a little bit of this framework for plugging in AI-RAN modules to the gNodeB. So DApps, as many of you are aware, are an established concept within ORAN. They're not an adopted standard yet, but the kind of agreed upon E3 interface is already implemented in OAI. I think that there are plans to implement that in OKUDU. For AI-RAN, the kind of constraint here is fitting this DApp RAN interface into the latency budget for kind of slot processing. So to kind of figure out which tasks can run, we have kind of places where we want to slot in plugins all the way down to the physical layer and all the way up to some sort of like advisory control where something like an XApp might be applicable even. So the work isn't just add DApps to OKUDU. We are kind of taking a broader view of classifying all of the use cases of AI-RAN as much as possible. I mean, to the extent that you can create kind of an ontology of these things. And sort of match each of these use cases to an interface that fits its budget. So the approach so far has been to kind of break down these use cases into a few different kind of classes. So what I've shown here is class C is kind of what is currently defined as a DApp in the literature. So these are things that are providing maybe telemetry or some kind of RAN policy, and they serve kind of an advisory role. They don't necessarily need to have like slot timing. And our colleagues over at, Tommaso is here maybe, and over at Northeastern have put a lot of work into, for instance, their E3 agent, which operates kind of at this level. But there are some sort of more timing sensitive applications like inline processing in the physical layer that not only need to fit this time budget, but also are processing a pretty large amount of data. So it's important that these interfaces, for instance, be able to keep GPU memory resident on the GPU. So these have to be pretty low-level kind of ABI-style interfaces in order to satisfy those constraints. And then there's something in the middle where we're not necessarily in the physical layer transferring a huge amount of data across GPU, but you may still need a little bit less latency than something like E3 can provide. So yeah, as I said, E3 is the right tool for one class of AI-RAN applications, but it can't carry these kind of data-intensive, slot-timed tensors through the stack. And really, our philosophy right now is that we can't dictate these interfaces. The only thing that we can really do is benchmark and try to make the case for kind of the best performing interface. And so, we're trying to put together a paper that kind of goes through the details of these use cases, the full list, and also some benchmarks that will hopefully become part of an open source repository that can be used to kind of justify some of these decisions. As far as Deepsig's role, so OKUDU is, and I should say, a home for DApp and AI-RAN reference designs. But this is one of the main focuses of Okudu, is to serve as a home for these interfaces, these plugin interfaces, and also a collection of reference designs, which Deepsig is, our goal is to provide those reference designs that really anybody can take and build upon to kind of make their own plugin, for instance, as a AI-based Mac scheduler, as maybe even a neural receiver, as just a kind of plugin that you load at runtime, you specify the appropriate configuration, and it goes. We want to make this kind of as little overhead as possible. As far as the OAI UE, how does that fit in? So the GNodeB is only half of the interface. In order to really do any system level evaluation, we have to close that link against the UE. Commercial UEs are not great. They're basically black boxes. We can't get any diagnostics from them. We can't get any sort of non-3GPP features. And so, yeah, we really need, as part of an AI-RAN stack, a UE that can be instrumented, that is able to be modified. And so that UE, at least right now, is the OAI UE. So the open source and kind of fully available for use in a test bed like this. So kind of 3 use cases for the UE. We can run it entirely in software. So radios add a whole lot of uncertainty to the mix. So we'd like to be able to do this all kind of locally on a system. We can drive it with reproducible channels. We can do all sorts of SNR sweeps and blur curves and things like that. And we can get metrics from both ends of the link. This is what allows us to start working on a learned physical layer. And I mean, all of this is nice because you can drop it right into an automated CI process, and you don't have to spend the kind of lab time and the complexity of bringing up an over-the-air setup in order to test these things. Kind of the second step here is that this can serve as a flexible over-the-air UE. So, okay, you take what you have on your test bed, you plug in a USRP, and now you get a full over-the-air setup that can now be instrumented. It begins to enable ISAC, as we've seen in a number of demonstrations here already. And you can kind of start closing the gap between the simulation environment and the real world. So in the real world, you encounter impairments, timing challenges, RF non-idealities that you don't necessarily encounter in simulation. And then finally, it's a kind of point where we can start plugging in potential 3GPP 6G and beyond features, as well as maybe some even non-3GPP features. So our interest at Deepsig for a while has been trying to drive these two-sided learned waveforms. Putting a neural transmitter on the UE and a neural receiver on the GNodeB. And so you get one kind of end-to-end system that is kind of outside the realm of standards, but maybe have some kind of domain-specific use cases that might be interesting. You can study other two-sided models. So I think I heard somebody mention something earlier about CSI compression. Yeah, all of this stuff is possible. Yeah, nothing you can do with an actual commercial UE. And then I'm kind of making the case that Okudu and the OAI UE gives kind of this full learnable air interface with that kind of commercial grade GNodeB. And I'll point out we've got, so this is another product of ours, a non-3GPP modem, but this is a learned constellation to deal with kind of jammers and other interferers. It's actually 4 constellations on top of each other that are transmitted in different slots of the OFDM waveform. But you can get some kind of pretty exotic looking constellations that kind of optimize around certain types of impairments, which, I mean, is completely impossible to do right now within 3GPP. Finally, we wanted a fully containerized end-to-end software simulator. So Docker Compose, bring up your entire stack, and be able to run end-to-end. So we didn't want hardware in the loop, and OAI UE fits this need. It's all open source. We can just kind of put all these pieces together. So when we started work on this, there were some challenges. So documentation was pretty sparse at the time. It has, as I'll talk about, gotten better. But there wasn't really much documentation on driving the OAI UE against a non-OAI G-Node B. Just some demos and talks at older OAI workshops. There were some issues with incompatibility between the way that virtual kind of network radio was implemented. So OAI UE, oh, this is actually backward, sorry. Okudu used a ZMQ request reply socket, whereas OAI used RFSIM. And so there were a couple options there. We actually ended up building our own native ZMQ support into OAI before that was merged into to mainline OAI. And once we actually were over the air, we kind of encountered a few different blocking and performance limiting issues. So just a couple, I mean, if you're a test bed engineer, you just start going through the list of things that you encounter. So for instance, right now to use OAI UE against an Okudu G-Node B with kind of all the kind of mostly default configuration, you have to provide a UE cap file, and otherwise the UE crashes. We are sort of investigating in detail CSI feedback because that's kind of particular interest to some of the ML-based scheduling algorithms that we're developing. So, all right, you turn on CSI-RS, and, well, Okudu G-Node B requests that the CSI are reported on the shared channel, okay, multiplexed on there. Well, that drives an assertion in the UE that causes it to fail. On the other hand, if you don't have CSI-RS, you don't get link adaptation. And so it's kind of a catch-22. We need CSI-RS for the link adaptation, and we need link adaptation for really being able to do kind of any interesting work within the scheduler. So, okay, we've got CSI on shared channel support now. We've also got being able to multiplex the CSI reports onto the shared channel, as I mentioned. Native ZMQ radio support in OAI, so that's great. It's kind of interoperable in that way. And there's a couple other little fixes pending, at which point, we will have come a long way in the last maybe 6 months or so. Finally, just kind of a summary here. Okudu, as I mentioned, is kind of built to host DApps and OpenAI RAN interfaces. And like, as I said, we hope that some of these interfaces can also be adopted in the OAI community so that we can sort of have a community standard for these sorts of AI RAN plugins. We have the OAI UE playing a few different roles. So it's useful for debugging and development of AI RAN applications. It's a flexible over-the-air UE for instance, for ISAC and other live experiments. And it's an integration point for 6G and maybe non-3GPP two-sided learned waveforms. And together, this is a complete kind of open, learnable air interface, kind of driven by OCUDU at one end and OAI at the other end. And to kind of conclude here, within the OCUDU ecosystem foundation, Deepsig has formed 2 working groups. And within the kind of Linux Foundation hierarchy, these are kind of relatively targeted groups of developers who are focused on kind of developing the framework for a particular kind of feature or kind of goal for the project. And so Deepsig here is leading a hardware acceleration and an AI RAN working group. So yeah, I invite you to kind of get involved if you're interested. And with that, I think I am at time. So thank you all.
Time for one little question. Any question? So yeah, a very quick one on the license, right? I mean, there is that concern from given the licenses are different. So can you say something about that?
Yeah. So OCUDU is licensed under kind of a standard BSD 3-clause license that permits kind of commercial products to be developed from it, kind of using permitting modifications of the code base in that sense. That's a requirement from the funding organization. So OCUDU is funded under the sort of National Spectrum Consortium, and that was one of the kind of requirements of OCUDU under that program. As we've heard a lot of people kind of talk about over the last day and a half, that is kind of maybe a controversial decision, but yeah, I can't really speak to the kind of motivations there, but the focus is kind of commercial applications.
Yeah, but you know, it's just that the fact that OAI is under a different license and UE also is under the same license is a bit of a question right now.
That's right.
That people are asking themselves. So maybe this is something for the benefit of the community can be said. We don't have a resolution right now, but you know, that's the state of affairs. Right?
I think so. Yeah, I think there's some interest in kind of both groups, yeah, kind of figuring out the path forward with that.
Thank you, Matt. Thank you.